So I've added to our course page a link for Matlab. Matlab is a matrix, it's a matrix tool where you basically collect numbers together in a matrix, and then you could do things like plot the values in your matrix. And so I think the best thing to do is to just start right up. So if you want to follow along, you can go to Start Up, All Programs, and then go to Matlab, and then you go out to Active Math. So it basically gives you an open area where you can type code in. I have some files saved away, and if you want to, you can copy them off of this course page. If you click on this link and then click on these different ones, you can cut and paste this code into your blank area if you want to follow along. Okay, so what I'll do, since I already have them coded up, I'm going to open all the existing files. Go to the directory where the files are. And the first simple one is a program that will display the string hello world. That's a popular in computer programming. The first program you ever learn is how to print out the word hello world. And actually, Matlab wants you to have an active folder, so I'm copying this out of a folder that's not my active one, so it asks me to reset. Okay, so nothing too interesting going on here. We just have a program that says display the string hello world, and that's what came out. Okay, nothing too fancy there. Just getting comfortable with using this one. Okay, so another program we could use would be, here's a program that you can plot a function with. So let's say I wanted to look at a function like, let's say I wanted to look at a function like this. The x-axis, here's the y-axis. And I wanted to have a function that starts at a 2. And it's the function y equals x squared plus 2. What I could do is I could say, I want to plot along the interval from 0 to 4. The function, so fplot is a Matlab function that plots a function. So this is x squared plus 2, and I'm plotting that against x. And you could also put, this is now going to create a picture. You could put a title into your picture, or a label for the y-axis, and a label for the x-axis. Okay, so if we wanted to plot this, you hit the arrow up here. This arrow means run the program. And a picture pops up. Based on the instructions, so for a pretty small amount of instructions, you can have a graph like this, and then these graphs can be saved as JPEGs, and you can take the JPEGs and cut them into your Word documents or reports. But what we basically have here is the function y equals x squared plus 2. Now it starts it off at the meaningful points. You could expand it to have more area, but since everything below 2 doesn't show up, it kind of cut that out. But you could add that back if you wanted to. Okay. So Matlab is not only so you can print out words like hello, it can plot graphs. So you could give it 2 vectors, a bunch of x values and a bunch of y values, and then just say plot, and it'll draw a plot for you. Excel does that too, right? You could just shade a region and plot the graph. Okay. Now suppose, And this will be an interesting, question. Let's see what answers you guys say. Okay, suppose you wanted to find out the answer to a question like this. You have a function y equals 2x. Right? So the function y equals 2x looks like this. What is y equals 2x? This looks like this, right? It's a straight line. Okay. If I wanted to know what is the value, what is the area from 1 to 3, what is this area? What would your answer be? So this is not a Matlab question, this is just a geometry question, I guess, from high school. What would your answer be? So this is from 1 to 3, and the height is 2. So what's the area of this box? Okay, so it's 2 wide, from 3 to 1, and the height is 2.
4.
So it would be 2 times 2 equals 4. Okay. What if we had a question like this? From 1 to 3, suppose we had a function like this. This is y equals x. And you were asked the question, what's the area between 1 and 3 under this curve? And not a curve, it's a straight line. What would your answer be? So this is a little bit harder than the last one. What would the answer to this one be? And more importantly, what are you thinking when you're solving? But what does this one come out to be? Anyone have a guess how they go about this? Well, the last time we did this distance is 2, and the height was 2, and we multiplied them together. We're going to do something similar now. What would we do? Well, the thing is the height keeps changing, right? The height isn't constant like the last one. The height is changing. But what could we do that's like 2 times something? What could we do? Okay, so what we could do is we could try to take the average height, right? This goes between 1 and 3 along here, right? The height is 1, this is y equals x. The height is 1 and the height up here is 3. So on average it's 2. Does that make sense? You guys take calculus or no? You have taken calculus? Okay. So then you can solve an even harder question than this, right? Oh, you don't remember? Okay. All right. So anyway, okay. What we could do is we could say 2, which is 3 minus 1, times the average height of this area. And on average, it ranges between 1 and 3. And it's a straight line, so it is on average 2. So it turns out the average height is also 2. This ends up being 2 times 2 again. So the area under here is also 4. Okay, so now here's the hard question that only people who took calculus would know, or people who know how to play around with Matlab could solve. So since none of you took calculus except one person, let's take the calculus. All right. So then none of you should know how to solve this, but we could use Matlab to solve it. Suppose the function went like this. Suppose the function was the one we just plotted, for example. Y equals 2 plus x squared. And it would go something like this. Now this is not a flat line, it's curving. Y equals x squared, and if you wanted to know the area under this this curve. Anyone? So if you haven't had calculus then, and you want to know the areas under functions, if the functions were not perfectly flat, it requires doing something like what we did where we keep trying to take an average of the heights and adding them all up. And that's something you learn in calculus. So the way you would solve this in calculus would go like this. So this is going to look like nonsense to most of you, but you would integrate from 1 to 3. You're adding up everything from 1 to 3 over function 2x. Oh, sorry, this should be plus 2. So this would be 2x plus 2. And the integral of this is function is x squared plus 2. Right? That's the function we're working with. When we integrate this, we're trying to figure out what is the area under this curve between 1 and 3. We would integrate it from x squared plus 2 would integrate from 1 to 3, which equals x cubed over 3 minus 2x. Evaluated from 1 to 3. Does this, any of this ring a bell? Yeah, okay. So this would be, what, 27 over 3 minus 3 equals 1 over 3 minus 1. Okay, and this is 9 minus 6. Okay, so if you're not familiar with calculus, that ends up being the answer to this question. And when you take calculus, this will all make perfect sense to you, so don't worry about this number. But the area under this curve is 12 and 2/3. Now, that's using a technique from calculus. What if we didn't have that technique, but we wanted to use the idea of saying, well, the range is 2, what's the average height? And just multiply them together. We could come up with some way to say, what is the average height? If I randomly pick the point between 1 and 3 and ask, what is the height? Well, that would give me one number, and then if I randomly picked another one, I have one here, and then randomly pick one, I might have one here. And what if I did this 10,000, 20,000 times, and then took an average? I'd have the average of the whole area. So we can do that in Matlab. If you didn't know calculus, you could do this. Okay, so what this code is doing, is it's saying, I'm going to run an experiment. I'm going to go from 1 to 3. I'm going to run the experiment 100 times. And now these are some functions that are in Matlab. So what I'm going to do is I'm going to pick a random number, and random with a parameter of 1. Random with a parameter of 1 means that you pick a number between 0 and 1. And then we're going to randomly pick a number between 0 and 1. And then we're going to, guys, can you keep it down? Thanks. So we're going to randomly pick a number between 0 and 1. We're going to then expand that random number between 1 and 3. So So it's going to randomly pick a number between 1 and 3. So we're really just going to multiply it by 2. Right? 3 minus 1 is 2. And then we're going to ask ourselves, what does the function equal? And then do this 100 times and take an average. And that's going to be the average height. So then we'll multiply 2 times the average height. And that will give us, on average, this answer. Now, do you think it's going to come out to be exactly 12 2/3? If I just, so basically what we're doing now is we're using Matlab to take random samples. So the question is, do we think it's going to, after 100 tries, do you think we will get it the average perfectly? And what this code will do is it will sum up all the samples, and then the error is going to end up being how wide it is by the average height, and multiply. So I'll run this experiment. And this time the answer came out to be, the area under this curve came out to be 13.15, which is not quite the answer, because the real answer that calculus gives you, the correct answer is 12 2/3. And running this experiment, taking 100 averages, taking 100 samples, taking an average, gave us 13.15. Now, if I run the experiment again, I can just keep clicking on. This time it came out to 12.15. And I could run it again, and now it's 12. Oh, that one came close. Okay? So what I'm really doing here is this. I'm solving a problem using Matlab. Matlab is where I code something up and I just take a bunch of samples and then take an average of the samples. I'm solving a problem that we actually, with calculus, we can actually solve because we know the real answer. So you wouldn't normally do calculus. I'm sorry, you wouldn't use Matlab to solve a problem you already know the answer to. But if we didn't know calculus, we could run this experiment and get answers that are pretty close. Now, what if I ran the experiment more often? Suppose instead of n being 100 times, suppose we made it 1,000 times. Then what would you say about the result we're getting? So if I took one, suppose let me do the extreme. Suppose I took one sample. I randomly picked a number between 1 and 3 and asked, what is y? And I said, that's the average. As opposed to doing it 100 times, which way would give more likely give a better answer. So it's when we do it 100 times because we're taking an average of more numbers. So if we went from, let's say, 100 to 1,000 experiments, right now this number n is how many times? I'm doing a for loop, so for 1 to 100, we're going to run this experiment 100 times and then take an average. Now suppose we ran it 1,000 times. We might not get answers that are so, these answers keep coming close to the real answer, but they're off by a little because we're not running enough experiments. So maybe if we ran it 1,000 times, let's see what would happen. Oh wait, hold on, let me change the number of experiments to 1,000 and then run it. Okay, so that came out to 12. Oh, that's it, perfect. Let's try it again. Okay, this one's not it, perfect. This is 12.71. And if you keep running this code over and over, and now it's taking 1,000 samples, you'll get a much closer answer. And then if I ran it, since the computers run fast, we could run this experiment 100,000 times, and hopefully should get a much better answer. So running it 100,000 times and then taking an answer, we got 12.6656. Run it again, 12.6658. 6737. So now I'm feeling more and more confident that I'm getting closer and closer to the real answer. So really what we're doing here is we're using a tool that generates random numbers Then we're taking the random numbers that we've generated that have some kind of meaning to us, and we're applying it to this function, x squared plus 2, to figure out what y is. We're summing up all the y's we keep generating. We've generated 100,000 values for y. We've summed them all up, and then divided it by 100,000 to get the average. And now we said, okay, now I know the average height of this function, the height from along the y-axis. I take that average multiplied by the x, and that'll be our area under the curve, and it becomes very, very close to the real answer. We'll never get the perfect answer, but it becomes very close. If we let the number of experiments go off to billions, then we'll get really, really close to the right answer. But we'll get an idea of where we are. Now, you would not use Matlab to solve a question that you already know how to solve. But are there things with experiments that you don't know the answer to, and the only thing you could do is run the experiment over and over and over and take an average? Is there anything in life you could think of that works like that? Well, it shows up in, it'll show up in scientific experiments where you don't have the answer, and the only way to get the answer is to run the experiment and have it 2 times. And that's what Matlab is used for a lot. It has other functions too, but that's what it's used for a lot. So, for example, we could have a what in a probability class is called a random walk. Okay, so a random walk in a probability class basically says if you start with you start at a position, let's say 0, and then you flip a coin, which has a 50% chance of being heads and a 50% chance of being tails. And if it's heads, you move forward 1 step, and if it's tails, you move backwards 1 step. And you flip the coin a number of times, let's say 50 times. Where would you be 50 time units from now? Anyone have a guess? Like, I mean,
Maybe like close to the same spot.
yeah, you would be expected to be, so that's very good. That's a common probability question. Where would you expect to be would be back at 0, right? Half the time you'll go up, half the time you'll go down. But you're not going to definitely be at that spot, but that's where you'd expect to be. How far away from 0 could you be? Well, in a really rare case, you'd be 50 units away. If you kept going heads, 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 heads forever, right? But that would be really rare. And tails, 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 you'd go to -50. But if you wanted to know on average where would you be, now you saw intuitively you'd expect to be at 0, right? But if I wanted to know where I would be and couldn't see that it's 0, I could run this experiment. So let me just will draw a plot of where somebody would be. So what I did here was, maybe I should put the code next to what was creating for us. Okay. So what this code is doing is it's saying the coin flips at a rate of 50% heads, 50% tails. I'm going to flip the coin 50 times, so this should go from 0 to 50. I start at 0, and now what happens is starting at 0, I'm accumulating numbers, I'm picking a random number. So here's the only part with Matlab, you have to come up with a little code for what the experiment is you're trying to do. So I'm picking a random number between 0 and 1. And what I'm doing is I'm multiplying it by 2. So let's say it picked 0.75. Multiply that by 2, it becomes 1.5. I subtract 1, and that means it's above a 1, so that's a heads. So I'm basically using the Matlab function random, multiplying its which prints out a number, which generates a number between 0 and 1. I'm multiplying it by 2, and then asking is this bigger than 1 or not. So that's simulating a coin toss. And then I'm doing a plot. And I'm thinking M is magenta. That's, you can pick the color of your plot, because you could start plotting graphs on top of each other, and you could change the colors if you wanted to. So basically what happened was, we started with 0, and the computer's just randomly generating whether it was heads or tails. and it went heads, tails, and a whole bunch of tails, went head, tails, bounced around here, then came back and ended up at 1, 50 units later. So as you said before, we'd expect to be around 0. Now I can run another experiment right on top of this graph, just by hitting the arrow. And I can even change the color if I wanted to. But now I've ran it a second time, and I'll run it a third time. Let's see. And I could actually run this experiment a bunch of times. Just keep hitting enter and run more lines on it. So now what's happening is I'm running a bunch of experiments, and this is, these are all different, what they call sample pads. But one ended here, one ended here, one ended here, one ended here, one ended here. And if I ran it enough times and took the average, I could figure out where I would expect to end up if I ran this experiment enough times. Okay, now, it seems intuitive, at least to one of the students, that you would end up exactly where you started. That's expected. Now, so mathematically, that's a really simple problem. If half the time you win and half the time you lose, and the amount you win and lose is the same, you could play this game 1,000 times, or 1,000,000 times, where would you expect to be? You'd expect to be right where you started. Now, what if you went to a casino game where you're expected to lose slightly? Let's say you went to a casino game where you only have a 48.5% chance of winning, which is a game like blackjack. If I made this probability instead of 50%, if I made it 48%, 8.5, what would we now expect? Let me clear this. What would we now expect to happen? So if you were asked a question, for example, suppose you wanted to play a game where you win 48.5% of the time and the casino wins 51.5% of the time, and you played it 50 times, how much money would you expect to have? What? A little less than what you started with. But how much on average would it be? How would you do a computation? Now that one, that's not as easy as the calculus question we did, but it's doable. But anyone have a guess at that? If you want, so here's the question. Last time we had a 50-50 chance. You have a 50-50 chance of winning. You play it all day long. Where do you expect to be? You expect to be where you started, right? You might win, you might lose, but you would expect to be where you started. Now, if we said you're playing a game where you only win 48.5% of the time, and you played this game 50 times, how much money can you expect to have? You might win, you might lose, but where would you expect to be? This becomes a very, very difficult math problem, but we could run the experiment tons of times and see what the result is. Now, if we run this tons of times, you're going to see sometimes you win and sometimes you lose. But I'll start a new graph. So this is a person who started off winning and then ended up losing a lot. And then I'll run it again. Now, if I run this tons and tons of times, should see a pattern. It's not developing. Let me try this. Let me make the game much more in the casino space, 40% of the time. I just wanted to show a pattern start. I'm going to run the experiment tons and tons of times. So this is like you went to the casino thousands of times and played this game. You start to see a pattern that it drifts downward. Right? You started at 0. Well, you don't start at 0, but you started with some amount. I should have said we started somewhere else. But anyway, we run the experiment. Sometimes we win, sometimes we lose, but there's kind of a drifting downward. And if you wanted to know, after 50 plays, where would you expect to be, you could just run this experiment 10,000 times and take an average. Start off how much money you have, run the experiment, and take the average. So this is a tool to conduct experiments, and they're not that hard. It's only, it takes a little while getting used to how to write this code, but it's not too many lines of code that can then conduct this experiment thousands of times, and you can see what the average is. And we'll go one other example. Has anyone heard of a scientist named Brown, a botany scientist from 200 years ago? I don't know if anyone's a biology major. So if you go to Wikipedia, these are graphs you can tell were generated with Matlab. I wonder if they even say that right at the bottom. So it's using, right here it uses random, generated random walks as I understood it. But anyway, there's a famous, what's the science of plants? Botany? Yeah. Okay. So a famous plant scientist named Brown from like, I think 1827, was studying what happens if a particle, pollen or something, falls into a lake and starts moving around. Wanted to know where are all the possible places it could end up. So where would the particle be at a certain point in time ends up being very close to where it was a little while ago, but since then it has moved a little bit. So what he ended up doing was using what's called a normal distribution. Does that come up in classes? Where? Right, a normal distribution ends up being like this. So this is really what is, by definition, what they call a Brownian motion. So it's named after this guy Brown, almost 200 years ago. But a normal distribution is when you take a random variable. It's not like a coin that's either heads or tails. It ends up being like this. You pick a number and you have a mean, and then a variance, how wide it can go. But it always ends up being in the shape of a bell curve. And then, I believe it's 1 unit sigma away from the mean is where 50% of the results are in the middle and 50% are on the outside. That's called 1 sigma, and then goes 2, 3, 4 sigma. So this ends up being a normal distribution. And so anything that's modeled by saying where you're going to be 1 time unit from now is where you were 1 time unit ago, and then we just randomly pick a number to see how far you've moved either up or down. Okay? I don't know if that intuitively makes sense, but so the random walk thing we did, we flipped the coins. We said wherever we are, it's our current, how much money we currently have, then either plus $1 or down $1. And we kept running that experiment over and over. If we instead said, let's take how much money we currently have and pick a random variable, where it's more likely we're going to get close to 0, if the mean is 0, the next location will be is where we currently were, plus or minus whatever we added here. So if you model it this way, using a normal distribution, this is called the Brownian motion. Now this comes up a lot in life, in normal life. And it actually comes up, I think on the wiki page, it comes up in the stock market. So the stock market, following the stock price, would say, what do you expect the stock price to be? Well, I expect it to be what the price was a little while ago, plus some change. And the change would be normally distributed. And then if you expect it to go upward because there might be some interest or the investors are expecting to make money, you could then just add some interest rate. So it goes on an incline like we've just done before. We had a decline. You would just add an incline. Same thing is true in tracking criminals running away. Criminal breaks out of jail, where do you expect them to be? Well, you expect them to be where they just were. There's a little more movement since their last time. So you can plot what's Brownian, what they call a Brownian motion. And so the Matlab code for plotting this, and this is a standard Brownian motion. And so we can set the sigma, right? By changing the sigma, we can make the bell curve be taller or flatter. You know, we can set the sigma to be wider, and then the bell curve would look something like that. And the closer you make the sigma, you know, meaning the more wild the next event is, the more movement away from where we currently are there could be. So I'm setting sigma to 1, but I have a variable. I can change that to something else. So I can plot the Brownian motion by hitting this graph. So this is similar to the one we just did with the random walk, except that it's not as jagged because that went on different intervals. And we either went up $1 or down $1. Now, our current location, our location is where we were at one time unit before, plus or minus something that came out of that bell curve. And then our next location is that location plus or minus something that came out of that bell curve. And so this is very similar, that I started it at 0, and I have the expected value is going to also be 0, and in this case it came out lower. So now what we can do is if you run this experiment on top of itself, over and over, something like this. So this is where we just keep running the experiment on top of itself. And if we wanted to make the angle of it go up or the angle of it go down, we can do that too. And so for example, if you had something that was a Brownian motion, which is, it comes up pretty common in life. So has that ever come up in any of your classes, the free Brownian motion?
No, just like the normal curve.
Okay, the normal. Okay. But yeah, so any time you needed, if you needed to conduct an experiment where something is moving around, and its movement can be modeled by saying where you expect it to be at time equals 5, is where it was at time equals 4, one time unit before, plus or minus something. And if that something happens to be normally distributed, meaning it's, which is a very common thing for things moving around, like pollen moving around in a lake would move like that. That could be modeled using something like this. And then with a tool like Matlab, just a couple of lines of code, you can go out to Google. You don't have to be like a Matlab genius. You can go out to Google and just look up, you know, Brownian motion or random walk and Matlab, and you'll find code snippets that do this stuff. It's actually very, very, very easy to have something like this come out. And then an example in like the stock market, you could say, okay, we wouldn't start at 0, but let's say there's some stock that's currently selling for $100. What do you expect it to be 1 minute from now? Well, pretty close to 100, but it may have gone up or down a little. But you would not expect it to go from 100 to 14 to 6,000. It wouldn't bounce around like that. Its value would always be very close to what it currently is, plus or minus whatever changed in the last minute. And then you model that change, and then you could say to yourself, like for example in the stock market they have something called a stock option, which means you get to get money only if the stock goes above a certain number, and below a certain number you don't get any money. And you want to know, what do I expect the value to be of my stock option? What you could do is you could try to model the stock using Matlab, run the experiment 100,000 times, and then ask yourself, not counting the ones below this line, just take the ones above this line and take an average of them, and that's what you'd expect to receive. And then you can decide whether you think it's worth it to
apply the stock, was a stock option in that case.